Hello, awesome students. This is Bert Dixon. We're going to do a few more examples of triangle proofs today. So typically it's best to kind of plan out the proof in your head and by marking up the diagram before you start writing anything in your proof. So our givens here, we have AD is congruent to BC. So the way we mark that is AD is congruent to BC. We can mark that way. And then we also know that segment AB is congruent to segment DC. So we know those two are congruent. And now we're trying to prove that line AD, which is this line, is parallel to this line. And so it looks like we would probably want to use this as a transversal. And so thinking ahead, how could we show that those lines are parallel? Well, we learned that if corresponding angles are congruent or if alternate interior angles are congruent, then the lines must be parallel by the converse of those parallel line theorems. And so if we can show, for example, that angle 1 and angle 2 are congruent, then that would be enough to prove that those lines are parallel. So let's think how we can do that. We know this whole chapter is on congruent triangles. So right now we have two pairs of matching sides in the congruent triangles. We also know that this side, DB, is in both triangles. So it looks like our triangles are congruent by SSS. And so if the triangles are congruent, then all the matching parts are congruent. So that would make angle 1 congruent to angle 2, and that'll be enough to prove that the lines are parallel. So now that we kind of have the proof planned out in our head, we can go ahead and start writing. And so we'll start with our givens. So we said AD, segment AD is congruent to segment BC. That was a given. And then another given, we have AB is congruent to DC, also given. And then remember, there are three pieces that we need in order to show that those triangles are congruent. So I'm going to write the other one right next to it. We said that segment DC is congruent to itself, and that's called the reflexive property, not DC, sorry, DB. DB is congruent to itself, and anytime you're saying that a segment or an angle is congruent to itself, that's called the reflexive property. So I'm just going to write reflexive here. It's technically the reflexive property. And those three facts are enough for me to say that the triangles are congruent. And so I'll say triangle ABD is congruent to triangle. Now we have to match up the corresponding pieces. AB matches up with CD, so it's going to be CDB. And we said that that's by SSS. So since I'm saying it's by SSS, I need to make sure I have all three of those parts. And that's why we have these three bubbles here. Whenever you're proving congruent triangles using SSS or ASA or SAS or any of those, then you want to make sure you have three bubbles pointing to the congruent statement because it takes three S's. So here's a pair of matching sides, here's a pair of matching sides, and here's another pair of matching sides. So that does give me the three S's that I need. And so that's why we have three arrows pointing to this one bubble, because there are three separate facts that lead us to this conclusion that the triangles are congruent. Now that I have the triangles congruent, I can say that angle 1 is congruent to angle 2, or I'm going to actually list those as using the letters. So angle ADB from the first triangle, notice that that's first, last, middle in terms of the order of the letters, is congruent to angle in the other triangle, first, last, middle, CBD, and that is angle 1. Those are angle 1 and angle 2. Those are congruent, and the reason why we know they're congruent is because those are corresponding parts of the congruent triangle. So that's exactly what we're going to write. corresponding parts of congruent triangles, or you could say congruent figures, are congruent. Okay, so that's how we know that angle 1 and angle 2 are congruent. And then from that we can say our conclusion, which is AD is parallel to BC, and that is the converse of the alternate interior angles theorem. And that is it. And if you didn't, if you don't know the actual name of the theorem, like the converse of the alternate interior angles theorem, you could just simply write out what the theorem says. You could say if alternate interior angles are congruent, then the lines are parallel. So that would be another way to write that reason. If you don't know the name of the theorem, the converse of the alternate interior angles theorem, then you could just write out what the theorem says. Okay, so that's it for that proof. Now our next example, I'm going to let you try this one, and you can do a 2-column proof or a flowchart proof. It's up to you. I'll demonstrate with both actually, so you can take your pick, whichever one you're most comfortable with. If you do a flowchart proof, make sure you have 3 bubbles pointing to the congruence statement. So pause your video, try this one out, and press play when you're ready to check your solution. Okay, so here are solutions. The first one is the 2-column proof. So before we start the proof, we should go through and mark up the figure. So when it says that BD and AC bisect each other, when BD bisects AC, that means BD is cutting AC into 2 equal parts. So I can mark those as equal parts. And then it says each other, so that means AC also cuts BD into 2 equal parts. So those 2 would be the same. And then we also know that angle 1 and angle 2 are vertical angles. So those are congruent, even though that wasn't given. Vertical angles are always congruent. And so now we see that those triangles are congruent by SAS. And if the triangles are congruent, then all the matching parts are congruent, and that'll give us enough to prove that AB is congruent to CD. Okay, so in the proof, I put both the givens on one line. You can do that, or you can put it on 2 different lines. It doesn't really matter. And then BE, we marked this and this. BE is congruent to ED, and the reason why we knew that is because it was given that AC was a segment bisector. And same thing with AE, congruent to EC. We knew that because BD was a bisector. So that's the definition of a segment bisector. And then we have AEB and DEC, or you could just say angle 1 and angle 2 are congruent by the vertical angles theorem. And that gives you 2 sides and an angle, and the angle is in between, so that's why it's SAS. And so the triangles are congruent by SAS. And since the triangles are congruent, then the corresponding parts are congruent. Okay, so that's what it would look like as a 2-column proof. Over here, I also have the flowchart proof version of that. Notice that I put the 2 bisector statements. I wrote those separately. BD bisects AC, because that leads you to the fact that AE is congruent to EC. And then this AC also bisects BD, and that leads you to this statement that BE is congruent to ED. So the segment bisectors were given, and then the next bubbles are what it means to be a bisector, that it cuts it into 2 congruent parts. And then notice that this angle 1 congruent to angle 2, there's nothing leading to this bubble because there was no fact that they gave us that led us to this. It was simply the diagram. We looked at the diagram and we said those are vertical angles, so those have to be congruent, and because they're vertical angles. And so angle 1 is congruent to angle 2 by the vertical angles theorem, and that gives us the 3 parts we need to say that the triangles are congruent. So here's our pair of matching sides, and here's our pair of matching angles, and that gives you SAS. And then once the triangles are congruent, then we can say the corresponding parts are congruent. Okay, so there's 2 different versions of that proof. Okay, and then example 3. This time we have angle C is congruent to angle B. And that's all that's given. And we're trying to prove that side AC and side AB would have to be congruent as well. And so remember I said this whole unit is on congruent triangles, but we only have one triangle here. So what I'm going to do so that I can work with 2 different triangles is I'm going to drop a perpendicular line. Remember when we did a construction that said if you have a point P off of line L, remember we swung our compass like this, and then we did the 2 marks like this, and we said there's the perpendicular, and there was a theorem that said there's through any point off a line there is exactly 1 perpendicular to the line. We're going to use that here. Through point A, there is a perpendicular line, and so we'll say let L be the perpendicular through A, so that's going to form a right angle, and then that's going to break that up into 2 different triangles, and we need to name this point, so we'll just call this point M. No, let's call it X. So this point is X, and so now we have 2 triangles to work with. We know since that's a right angle, that would have to be a right angle as well. And then we have a pair of matching sides. AX is congruent to AX. And so now we have angle, angle, side. And so that's enough to say that those triangles are congruent by angle, angle, side. And once we have the triangles congruent, then that means the matching parts are congruent. So I'm going to write this up as a flowchart proof. So first we have angle C is congruent to angle B, and that's given. And then we said let L be the line through A that is perpendicular to CB. And the reason why we can do that is through any point not on a line, there is exactly 1 line perpendicular to the given line. Okay, so that's a lot of writing for a flowchart proof, but kind of need all that. Those 2 things are unrelated. That's why I don't have an arrow connecting them. And then we're going to say let X be the intersection of L and CB. And you can just say all perpendicular lines, or we can just say 2 perpendicular lines intersect at one point. Okay, and so now we have everything we need, I think, to start working on the triangle congruence. So we said angle, we'll say angle 1 is congruent to angle 2. Or maybe I'll break that into two things. I'll say angle 1 is we'll say angle 1 equals 90 degrees. Measure of angle 2 equals 90 degrees, and that's the definition of perpendicular. So the perpendicular lines led us to that, and then we can say angle 1 is congruent to angle 2. Definition of congruent. Angles with the same measure are congruent. Okay, so now we have angle 1 congruent to angle 2, and we can also say that AX is congruent to AX. That's the reflexive property. And now, putting those three facts together, we can say the triangles are congruent. So triangle ACX is congruent to triangle ABX by AAS. And that came from these three parts. That pair of angles, that pair of angles, and that pair of sides. So now that the triangles are congruent, we can say AC is congruent to AB because corresponding parts of congruent triangles are congruent. And we're all done. Okay, so that's that one took a little bit of time and maybe some different techniques than we've used in the past, but this is a really important result because it says if we're given, think about what we started with, if we start with a triangle and it has two angles that are the same, then that leads us to the conclusion that the sides across from them have to be the same as well. And that is the converse of what you proved earlier today. We proved the Isosceles triangle theorem, which said if two sides are the same, then the angles across from them have to be the same. So that was the Isosceles triangle theorem. We just proved the opposite of that, so that's the converse. So the converse of the Isosceles triangle theorem would say if the base angles of a triangle are congruent, then the triangle is isosceles. Or another way to say that would be if two angles of a triangle are congruent, then the sides opposites those two angles are congruent also. Okay, so there's two different ways to state the converse of the isosceles triangle theorem. And that's it for today's lesson. Have a great day.